Okay, so I want to talk about mapping patterns for real-time knowledge graphs. Stefan already said this is joint work with Avigdor from Haifa, with Davide Lanti, Marco Montali, and Alessandro Mosca from Bolzano, and with Roee Shraga in Haifa together with Avigdor. And this is essentially ongoing research that we are doing here. Now, the setting, I don't think I want to spend much time since we already talked about it. The setting is that of virtual knowledge graphs where we want to access data sources using an ontology. And the aim here is to come up with a specification for such a system. We call it virtual knowledge graphs, but it's essentially a rebranding of OBDA, ontology-based data access. Now, an important component of such a system are the mappings, the VKG mappings, which map complex queries to complex queries. So in this sense, they are similar to GLAV relational mappings, which have been studied in the relational setting since many years already. The idea is to overcome the abstraction mismatch between relational data and target ontology. So that's a difference between the pure relational setting. And such mappings are also inherently more sophisticated than mappings used in other scenarios where one matches or combines different sorts of schemas, for example, in schema matching and ontology mappings, where also mappings are studied. And as a consequence of the combination of these aspects, it turns out that management of VKG mappings is labor intensive and essentially a manual effort. And it requires highly skilled professionals to be done in real world scenarios and real world use cases where we might have very large ontologies, very large databases, possibly thousands of mappings assertions. So this is a challenging task in terms of semantics, correctness, and also in terms of performance of the result that one then achieves. So it turns out that designing and managing mappings is actually the most critical bottleneck for the adoption of the VKG approach. And we want to do something about this. One proposal that we are not the first one to follow it is to support the creation of mappings in the VKG setting by means of patterns that give us common structures for such mappings. And in fact, there are several works that present some forms of patterns for mappings also in this scenario. But our study identified that there is essentially no comprehensive approach of VKG mapping patterns that exploits all of the following elements: the relational database schema with its constraints, the extensional data stored in the database, the ontology and the T-box axiom that constitute the ontology, and also the underlying conceptual schema that is at the basis of the relational database that we want to map to. And all these elements, they somehow play a role. And in this work, what we did is we propose a catalog of VKG mapping patterns that rely on these four elements, where each mapping pattern is distinguished by these four elements. We also discuss some design scenarios for the use of these VKG mapping patterns and how they can come into design scenarios related to VKG. And also we did an extensive analysis of practical VKG use cases in terms of the usage of these mapping patterns. So let me briefly talk about these 3 points. First of all, the catalog of mapping patterns. Now, in order to set up our catalog, and the elements in this catalog, so the patterns in this catalog, we are building on well-established methodologies and patterns that have been studied in data management on one hand, in data analysis, and also in conceptual modeling. For example, our mapping patterns capture the V3C direct mapping specification and also extensions that have been proposed for it. And what we do in specifying each patterns, we consider, first of all, the 3 components of the VKG specification, the database schema, the ontology, so the T-box axioms, and the mapping between the two. And then also, and this is a new element in our proposal, we consider the underlying conceptual schema of the domain of interest on which essentially we assume that the database was built. And also, when the data is available, we try to exploit the underlying data. And in fact, some of these patterns are precisely based on looking at the data when it is available clearly. Now, in what we present here, we do not fix what is given as input and what is produced as output, but we simply describe how the various elements relate to each other on a per pattern basis. And then, I mean, what is given as input and what is produced as output relates to the various design scenarios of the mapping patterns, of which I will talk in one slide in a second. In our mapping patterns, we distinguish essentially between two major groups. The first one are the schema-driven patterns, which are shaped by the structure of the database schema and its explicit constraints, so given the database schema. The second type of patterns are so-called data-driven patterns, which consider also constraints that emerge from specific configurations of the data in the database. And in fact, we have for each schema-driven patterns, we have a corresponding data-driven version where essentially the constraints of the schema might not be explicitly specified, but nevertheless hold in the data. There are many situations in which a database doesn't have explicit constraints specified, for example, for performance reasons, but still we know from the domain semantics that these constraints hold over the data. And this, for example, can then be exploited in data-driven patterns. But we have also data-driven patterns that do not have a schema-driven counterpart that relates specifically to the structure of the data. In our patterns, we also might use additional semantic information, and this leads to the notion of pattern modifiers. And some patterns come with views over the database schema that we can imagine if you apply the pattern essentially to a given set of relations and constraints, we might generate some views out of it to which then further mapping patterns can be applied. This is the idea. The constraints that we use on the data are the traditional ones, primary key constraints that we indicate by an underlying the key constraints, which go beyond the primary key. I mean, we might have additional keys that we want to consider, and then foreign key constraints, which we, in the next few slides, I will just depict some examples depicting the foreign key with an arrow. And also I use normal font to denote single attributes, whereas a bold font denotes actually a set of attributes. So typically in our patterns, we make use of sets of attributes. Now, we have identified several types of mapping patterns. I don't have time to discuss all of them.
Yeah, we also have to end soon.
So how much do we have? A minute?
Half a minute.
Okay. Each mapping pattern is specified through the 4 different elements. And I will just show you an example where you see we have the constraints, we have a conceptual schema, we have the mapping assertion that corresponds to the patterns, and we have the ontology axioms that are involved. And this is, for example, a traditional mapping pattern involving a relationship that gives rise to a role and with corresponding domain and range axioms in the ontology. This would be a variation of it with a modifier. We have various scenarios that are related to how we want to, which is given as input and which is given as output. For example, bootstrapping, where we are given a database and an ontology and we miss the mappings between the two, and other scenarios. And finally, we have considered several application domains and use cases where we have applied our patterns, and we have essentially identified 1,500 mapping assertions to which our patterns apply, and we have seen more than 300 different applications of these patterns. And we are currently working on using our patterns for essentially mapping, bootstrapping, and generation of mappings, also using the data and using learning techniques over the data. Thank you.